Hello students, welcome back. Now please remember, we are doing Math 3680, not 1680. So we need some advanced mathematics here, including some proof problems. And some of them will be answered here through this video. Now, the first half of this video is going to be required portion, and the second half will be optional. And I'll tell you exactly what is required and what part is not. Alright, let's begin. Here is a reminder, axiom of probability, and this is the addition rule that we are going to be using. That's where pretty much everything is coming. Alright, maybe I should copy and paste this thing. Okay. And then here are the rules of probability and addition rule. We have two mutually exclusive events, and then the probability of the union is the same as the sum of the probabilities. Now, what does the axiom say? The axiom said probability of infinite union is the sum of the infinite sum of probabilities. Here we have only two sets, two probabilities, so they're not exactly the same. How do you use this axiom to prove this? Well, this is written in a little bit too fancy a fashion, so let me rewrite it like this. Probability of A1, and then disjoint union, A2, disjoint union, A3, one more, and then dot dot dot. That's the left hand side, and then right hand side is infinite sum. Alright, this axiom, the third part of the axiom, third statement of the axiom is the same as this. And then can we use this to prove this? Here we have infinitely many, and use this to prove just for two sets. Yes, we can by doing this. A, okay, let's keep it as A1, as A. B, let's put it in A2 place. And for A3, I'm going to select the empty set. Where's the empty set symbol? This is not an exactly empty set symbol, but let me use it. Okay, I want to have some patterns, so let me put one more. Then that's the same as, I replace A1 by A, oh, this should be B. A1 by A, so A. And A2 by B, so B. And then A3, I replace it to empty set. And then the next, A4, I replace to empty set. And this is what I'm getting, basically. Now, what are all these? These are all empty sets, right? Just taking union of all those empty sets will not change anything. So this part all just goes down, and then we just have just these two. And then how about all these? All the empty sets, they all have probability 0. So they all go down, and we get down to this, which is precisely what we wanted all along. So that's the process we have. Here's a little bit more elegant version of the proof, a little bit more simplified version of the proof, basically. So A union plus B is the same as A union plus and then union plus a bunch of empty sets. Yes, empty events are mutually exclusive to everything because there's no overlap, because there's nothing to begin with. And then we can apply the axiom. Because we have infinite union here, they're all mutually disjoint, so we can add up the probabilities and then look at all those empty events. We're adding a bunch of zeros. So yes, we end up with probability A plus probability of B. Tricky? Well, that's a proof. So, one of the morale is any infinite union or any infinite sum can be reduced to finite union or finite sums by simply adding up zeros, bunch of zeros. So taking union of a bunch of empty sets. Next, how about this? Well, this is not too difficult. I mean, for once, this is an easy proof because you see, A union B is just union plus of these three. So by the axiom, you can simply just add them all up. So A union B, you can simply add up the probabilities. Of course, if you really want to reduce that infinite sum into finite sum, all you have to do is take the unions of a bunch of empty sets and add a bunch of zeros. I already did it in previous proofs, so I'm not going to bother here. So that's easy. I can decompose and work it out. Okay, so far so good. Now how about proof of this one? This, I'm afraid, is not that simple. I have to use what you call that the axiom, right? So it is necessary that I decompose everything to disjoint sets or mutually exclusive events. Here, these are not mutually exclusive. A and B are not mutually exclusive. There is an overlap. So how do I fix it? Well, one way to do it is this way. A can be decomposed into this crescent region and football region. They're mutually disjoint, so you can add them up. And B can be decomposed same way. The football region, purple, plus this red crescent region. They are mutually disjoint, so separated. So A, B, both of them can be separated like this, or decomposed like this. Now they're union plus. So crescent plus football. Here for B, crescent plus football. And then we can apply axiom 3. So you can add up the probabilities. Are you with me here? And then add up these two. So probability A plus probability of B. So adding all these. This blue purple and red purple. So the purple part is added twice, right? Now this part here, as we proved before, is just probability of the union. So this part is the same as the probability of that union. So this part is actually we proved that. So you can replace this one by union. That's what I'm going to do. This part, there you go. I can replace it by something equal. So from here, this part, which I just highlighted in bold, becomes this bold highlighted part. Okay, and then it's easy now. I can flip this over to the other side. By subtracting, you're going to get to the conclusion there. And that's what we have in this proof. So here, pay attention to that bold part. That's what we have. Yeah, so I'm going to put bold part over here. So this bold part became this bold part because of that. And finally, let me find out this bold part by flipping this to the other side. We have the conclusion. So that completes the proof. Okay, how about the complement thingy? Okay, alright. This one is really easy. So how do you prove it? Well, if you take the union of A and A complement, it's just the entire sample space. That's the definition of this complement event. And then, of course, they are union plus. They are mutually exclusive. So I can separate and then take the sum of the probability. And then that is the same as probability of the entire sample space, so it's 1. So what's the conclusion? If you add up, you get 1. So subtract from 1 and you get what you want. So this one, you should be able to complete it and, well, out of scratch, basically, because this one is easy. This kind of thing, maybe a bit complicated. Okay, and then we have inequality rule. When A is a subset of B, then probability of A is less than or equal to probability of B. And look at the picture, it's really clear, but the proof is not that simple. And this kind of proof problem will be pretty much appropriate for about exam level proof problem, I think, because it's not super difficult, it's not super long, but there is something to think about, and then you have to use the axiom to work it out, you see? And there's no axiom associated to the inclusion subset thingy. The axiom is all about disjoint union, this union plus. So how do we work it out? Well, let's make this observation. B can be written as A, and then where's that union plus thingy? Mutually exclusive union of this and then B, but not A. So what is A? This blue or kind of purplish part, and B minus A is actually this outside. It's not precisely a donut shape. It's this A is kind of tilted, but anyway, that's the red part. All right. So probability of B is therefore probability of A plus probability of this crescent. See this? This is blue part, and B minus A, that's the red part. Now, let's make this observation. Let's keep this thing the same. Let's keep this, well, let me copy this entire thing here. They're the same, of course, because I didn't change anything. But here, let me change this probability into 0. Then what happens? Any probability is greater than 0, so this is greater than 0. So I ended up reducing this size. Why did I lose this? Why did I lose color? It was blue and then keep red. So what did I do? The blue part, probability of A, stayed the same, but I replaced this probability by 0. And consequently got smaller. And this is a kind of technique that's quite uncommon to most of the students who went through some proofs. It's an algebraic proof, yes, but using equality is one thing. Using inequality is useful. Using inequality is often more difficult. So here, I just replace probability by 0 and then go to the axioms of probabilities over there. Probability is always greater than 0. So that one, yes, is coming from, those 3 axioms of probability. So what do we have in the end? Probability of B is greater than or equal to the probability of A, and it comes from those 3 axioms. So that's the proof, and as a matter of fact, I have full proof here. Okay, that's it. And then finally I have one more, but oh boy, this is really hard. So I'm not gonna try the complete proof of this. Instead, I'll give you some guidance and then keep the rest as your own thinking. And if you're really interested in this kind of thing, maybe you can revisit after taking real analysis 1 or while taking it. So here is the first adjustment. Instead of A1, A2, A3, all those, which may have overlaps here and there as you have this kind of visualization, we defined a new sequence, B1, B2, B3, and so on, like these. So from B1, B1 is equal to A1, and then B2 is A2 set minus A1. So what is it? Let's see, this is a little bit confusing here because we have A, B, C's. Let me risk changing things around here. Okay, let me rewrite this one as A1, A2, okay. Okay, all right, I redid all those. So in this picture, I have only 3 sets, but in general, you have to repeat this idea. B1 is same as A1, so it's entire red circle, all right? Now B2 is A2 minus A1, so not the entire blue circle. You have to take away A1 part, so you get only the crescent part. Only the crescent part. So if you take union of these two, same as A1 union A2, but B1 and B2 are mutually exclusive because I took the set minus and I got only this part. My mouse is running it. B1 is same as entire A1, B2 is just this. And then B3 is A3 and the set minus everything so far. So A3 is this one, but not the entire thing, but A1 union A2. So this part, this figure 8 part is out. So we have only the outside part left. So basically, each of this Bn is only the outside part. So if you take union of all those, then same as previous union, as A1 union, A2 union, and so on. But in the end, they end up becoming mutually exclusive. And then each Bn is subset of An. So we end up with this. Same as before, so that's union 2. But then again, this is U plus, so you can apply the axiom and separate, add them up. And then Bk is subset, so this is bigger, consequently proving what we want. That is a sketch of proof.